Hi there, and welcome to another burst session. My name is Janice Novikowski. I'm a district teacher consultant for the Richmond School District in the areas of mathematics and numeracy. This is the first part of a four-part series on cognitively guided instruction. And today we are going to be providing an overview of what cognitively guided instruction is, specifically for British Columbia K-5 mathematics. To begin with, cognitively guided instruction, that's what CGI stands for. So you'll often see CGI embedded in our year plans and week plans, etc. And that's a sort of a pedagogical strategy for teaching the operations. It stands for cognitively guided instruction. So it is a sense-making approach to the teaching and learning of number operations. So addition, subtraction, multiplication, and division. It's really focused on contextualizing those operations. So students are using context familiar to them, similar to word problems, and the actions and the structure of those particular operations. There's decades of research to support CGI practices, began in the 70s and 80s from the work of Dr. Thomas Carpenter and Dr. Elizabeth Venema, and their research around how children develop their mathematical thinking as they engage in materials and use of operations through problem solving. And that has developed now and expanded, across North America. One of the epicenters right now for the research is University of California, Los Angeles. Just in case you're interested in sort of the research and evidence base for cognitively guided instruction. It is really grounded in mathematics education research, as well as cognitive science and psychology in terms of emphasizing how children think and how children learn. So where do we find CGI, or cognitively guided instruction, in our BC mathematics curriculum? It lives in the areas of computational fluency and algebraic thinking. And in the primary grades, we don't often think that we're actually doing algebra, but we are. We're developing algebraic thinking. Whenever we're sort of, 4 plus what equals 10, that is algebra. And that's those foundations for algebraic thinking, figuring out the missing part and looking at those different structures. So, for example, this is in grade 3. There's a learning standard, one-step addition and subtraction equations with an unknown number. And when you click on the elaborations for that I'm sort of circling here with my cursor, start unknown, change unknown, result unknown, that is all the language of cognitively guided instruction. So the research from cognitively guided instruction was embedded in the development of our curriculum in British Columbia. It also lives in 2 curricular competencies, specifically developing, demonstrating, and applying mathematical understanding through play, inquiry, and problem solving. And again, this is a problem solving approach to teaching the 4 operations. And then also develop and use multiple strategies to engage in problem solving. So again, students may have one strategy, but how else could they solve this problem? And it's this understanding of the different strategies that students use and a bit of a hierarchy or continuum of those strategies to help us know how to support students moving forward with their learning. So these are some of the books that you might be familiar with, either in your school professional libraries or available from our district resource center. So the one on the left, Children's Mathematics, Cognitively Guided Instruction. This is the second edition. The first edition was a bright blue cover. Some of you might remember that. It came with a little CD-ROM inside of it. This one has QR codes to link to the videos for you to watch. If you don't have one in your school library, I did confirm that there is one at the District Resource Center. If you teach kindergarten, this book here, Young Children's Mathematics, is specifically focused on 3, 4, and 5-year-olds, so that might be of interest to you. And then the 2 books on the right really extend the basic work of children's mathematics. The first book, Cognitively Guided Instruction, to look at fractions and decimals. So for those of you that teach grade 3, 4, 5. And then Thinking Mathematically really makes that connection between operations or arithmetic and algebra, and how that fluency and flexibility we want in children's mathematical thinking is really rooted in that understanding of algebraic thinking as we're operating with numbers. Again, the UCLA is sort of the epicenter right now of the research around cognitively guided instruction. And these are just some of their principles and things that they use to inform their research practices, as well as their classroom practices in sites around the Los Angeles area. I think that these core beliefs are really essential to an understanding of cognitively guided instruction. There's a core belief that children are competent and capable, that every student comes to math knowing some mathematics. They're not a blank slate. They've had experiences in their life, and we can build on those. Every student is capable of extending their mathematical ideas and growing as a mathematician. And again, paying attention and that sort of pedagogy of noticing and listening really helps us know where students are and how we can support them moving forward. And again, it's really about paying attention to the students' thinking, what they say and what they do, to help us support our instructional decision making. And again, we want to make sure that we're not using deficit language when like, oh, they're not able to do this or they won't be able to do this, that we want to really challenge the language we use and the assumptions we make about students and particular groups of students. And then really wanting to create space in terms of honoring all the different ways that students can participate and engage in mathematical thinking. So thinking about access points, thinking about identity, thinking about culture and community and family connections to mathematics, and how we can open up mathematics to create space for all of the learners in our classroom. So those principles are sort of really, behind the math or holding up the math in terms of welcoming children into cognitively guided instruction. So one of the key tenets of cognitively guided instruction is this idea of strategies and really paying attention to what strategies students are using. And there is a bit of a hierarchy in what we know about children's development. So that sort of first stage is the direct modeling of the actions or the relationships between the numbers. So that might be using their fingers, or it might be using counters, or it might be moving materials around or other manipulatives around to directly model the equation or the problem. And then the next one is counting strategies, which includes counting all, counting on, skip counting, and using multiples. And then from that comes derived number facts. So I know this, so I can figure out this. So I might not know 9 plus 7, but I know 7 plus 7, so I can figure out 8 plus 7 as an example. And that holds true as well for multiplication and division. What the researchers have found is that most children go through these three sort of stages of strategies as they engage in new mathematics or new number ranges. So for example, in our curriculum, a child working in grade 1 with addition and subtraction, within 10 and then within 20 would probably start with direct modeling. So combining those numbers or combining, some blocks or removing some blocks to model what's happening in the math story or the math problem, and then move to counting and then move to derived number facts, possibly by the end of the school year. When they move to grade 2 or grade 3 and they bump up to 2-digit numbers and 3-digit numbers, they might start at direct modeling again because the number range has increased. So whenever you change something, whether it's the operation or the complexity or the number range, you may have students again going to direct modeling and then moving to counting and then moving to derived number facts. I think one of the things we have to be careful about with our grade 4 and grade 5 students is that when we're introducing new content like decimals or multiplication of 2-digit numbers, etc., that students aren't going to just jump to derived number facts or, procedures. They need that direct modeling experience to understand and move through that understanding of those operations. And again, there's decades of research to support that. Again, another, important tenet or component of cognitively guided instruction is the 3 different problem types. And again, these can be used for addition, subtraction, multiplication, and division, single-digit numbers, triple-digit numbers, quadruple-digit numbers, decimal numbers. It doesn't matter. The same problem types, those structures are really important. And this is where that algebraic thinking comes in. That result unknown structure, 7 plus 5 equals what? That could be a blank, a box, an N, or an X. And that is where that algebraic thinking comes in, that missing part. That is the most common one and the easiest cognitively for students to figure out. That is what students see the most, whether it's at school or whether it's at home, on devices, where they might see it in workbooks, that type of a thing. So we want to make sure that it's not the only problem type or structure that students are seeing. They also need to see change unknown. So 7 plus what equals 12? Or start unknown, what plus 5 equals 12? And start unknown is the most cognitively demanding problem type of the three. And so, when I was in the classroom, I would just make sure I had a little bookmark by my desk just to remind me as I'm presenting different problems to the students. And we would do this probably about once a week. I would make sure that I was changing up my numbers and changing up the problem types to making sure that I was getting at all three problem types. So here's one example from one of our grade 1 classes. This was over at Cook, I believe. Cook or McNeely, one of them. And it was after recess. And so we just chose a context that was connected. This was in probably about October or November of the school year in a grade 1 class. So just sort of beginning to think about addition and subtraction within 20. And so I presented the problem or story. At recess, I picked up 9 leaves. And again, we have a lot of English language learners in the class. I had brought some leaves from outside, so I showed the leaves. I did the gesturing of picking up the leaves and putting in my hand. And then my friend gave me some more. And so we've got that underlined in question mark. That came afterwards. Originally, it just said some more. And then now I have 14 leaves. How many leaves did my friend give me? And so this is a change unknown problem. This class had already done some result unknown, and this was going to be a challenge we knew for some of the students, but we wanted them to think about this. And again, we didn't say much more other than what is it that we're figuring out? We want to figure out how many leaves that friend gave us. So that's why we underlined the word some and put the question mark, again, as a visual prompt to support the learners in that particular class. We read it orally multiple times. We read it together, by pointing to each word. But again, it was the oral story for these grade 1 students at the beginning of the year. We wanted to read it enough times that they would just have it sort of memorized and embedded in their heads. So again, each child was solving the problem on their own. Of course, there was some collaboration, but these are, some examples of the different ways students solved. So again, there was 9, and this student counted on, and they used their fingers. So this was the way they represented that. They started with 9, and they counted on, well, there's 14. So 9, 10, 11, 12, 13, 14. And then they held up, well, that's 5 fingers or 5 leaves. And then they put their little 5 in a box. This was another student who originally drew the 9 leaves, and then they counted on and drew like 11, 12, 13, 14, 15. And then they circled the 9 first and then circled the other part as the 5. And you can see that they've also drawn a little picture of the story of the action that happened. I had 9 leaves. My friend gave me some more. Now I have 14. So again, regardless of what grade level you're teaching or what operation you're using, you may see examples of how students solve the problem in these different ways. This is an example of a student who used some materials. They took the materials and actually traced them to create a drawing. But again, they've got the parts. There were 9. They counted on, and he actually wrote his strategy. So naming the strategy is also a part of this and is part of our BC curriculum. So I use counting on, and then you can see there that it was 5 that they added to make 14. And they've labeled it like here's 9, here's 5, and that makes 14. Another example of that was using 10 frames as a structure to support the thinking. On the left, the students used some 10 frames we had. They built the 14 because that was the total number of leaves they knew they had. And then they remembered that the child first had 9. So they used the structure of 10 and took 1 away from that. So there's 9 for one part, and then they just put that extra 1 with the other 4, and that made 5. So they use concrete materials, but direct modeling of the problem. And then on the right, the same thing, they drew the 9 leaves, and then they added to their 10 frame till it added up to 14. And then they colored in that additional part that came in, so parts and whole. This is a student that knew that he did it mentally. So he knew that 14 subtract 9 was 5. And so he used 10 frames again to sort of share his thinking around what he did in his head. And so he had 14 and he saw the 9 and he knew that there was 1 missing. So that would add to the 4. 14 to make 5. And so he used, again, 10 frames as a structure. So he was using, derived facts. He had already was thinking about the relationship of addition and subtraction. And again, you have that range of students in your class, and he represented his thinking and what he did in his head using the 10 frame structure. So that's just one example from a class. And then some other ways that we've, extended the use of cognitively guided instruction is creating math stories and math stories that connect to place and identity. So again, just some story materials. And you can see this was in a grade 2 class, and I've got different equation types. So these are the different problem types. They're 2-digit numbers. I also have some single digits and some triple digits in there because there's a range within your class, but I use those equation cards all year long. When I can show you on RichNet and on my district blog where you can download those and just print them off on cardstock, and students choose equation cards that are a good fit to them and then create their own math story or math problem using that mathematical structure or problem type to get started. So again, where you can find some connections to cognitively guided instruction in our numeracy foundations frameworks are in computational fluency and under mathematical thinking. There's a section on algebraic thinking, which is where this is all making this all come together and connect. And then some examples from the frameworks as well. In our week plans, we'll often have, do a CGI problem to assess whether students can apply and transfer their understanding of one of the operations or concepts. So when you see that, now you know what CGI is. On the right-hand side, you'll see when you go onto RichNet to the mathematics and numeracy page, you see the 4 frameworks, and then you see a little more info. There's some materials from my blog that have been transferred to RichNet, and one of them are all the resources on CGI math. So there's previous presentations that I've done on CGI math, and as well as those downloadable equation cards that you can access there. And then some extensions from the CGI research, choral counting and counting collections, both came out of UCLA. And their research extending the work around cognitively guided instruction, as well as numberless word problems. And if you haven't heard of those 3 routines, they're short videos, all available on our numeracy YouTube channel. The numeracy playlist has a whole series of those routines, but these 3 ones in particular, come from the CGI research. So as we finish the session together, just some things for you to consider. What can CGI offer as an approach to teaching to the diversity of the students in our classrooms? How does CGI support mathematical connection making between operations, so between addition, subtraction, multiplication and division, multiplication and addition, etc.? And what might be your first or next step in teaching using CGI principles? Thank you.